Good morning, students. Today we are going to study about potential functions. There are two types of potential functions. One is vector potential, another one is scalar potential. Okay. So the vector potential is denoted by the symbol A vector. The scalar potential is denoted by the symbol V. So let us study it in detail. Okay, so first let us write the equation that relates the vector potential with the magnetic flux density. So that is magnetic flux density B vector is equal to del cross A vector. So let us take this as equation number 1. Now substitute equation number 1 in our Faraday's law. That is our first law of Maxwell's equation. Okay. So let us write the Faraday's law, that is del cross E is equal to minus dou B by dou T. So in this equation, substitute the equation number 1, that is minus dou by dou T into del cross A vector. Now let us interchange these two. That is minus del cross dou A by dou T. Okay. Now bring the right hand side term to the left hand side. Okay. So let us write the left hand side also. So bring this to the left hand side. That is del cross E vector plus del cross dou A by dou T, that is equal to 0. Now in both the terms we have del cross in common, so we can take it outside the bracket. Del cross E plus dou A by dou T, that is equal to 0. Okay. Now look at the equation. We have del cross a term inside the bracket. Okay. So this del cross, that is curl of any term, if that is equal to 0, then we can say that the term inside the bracket is curl free. So we can say it as curl free. Now, if any term is curl free, we can write that term as, can write that E plus dou A by dou T term as minus a gradient of a scalar. Okay. So here the scalar we used is the scalar potential V. Okay. Now keep the E alone in the left hand side and bring this term to the right hand side. Now the equation will become E vector is equal to minus del V minus dou A by dou T. Okay. So this equation, take this equation as equation number 2. Okay. Now with the help of this equation number 1 and equation number 2, we are going to find the non-homogeneous wave equations for these two potentials. Okay. So let us write the heading of non-homogeneous wave equations. So let us find the non-homogeneous wave equations for vector potential alone first. Okay, so let us find it for A vector. Okay. So for that, first take the second law of Maxwell's. So what is the second Maxwell's equation? It is del cross H is equal to J plus dou D by dou T. So in this equation, substitute equation number 1 and 2. Okay. So the equation number 1 is B, the equation number 2 is E equal to. But The thing is, here in this equation, we don't have E or B. But we know a relationship that we have studied in the previous video, that is, B can be written as mu H. Am I right? And again, D can be written as epsilon E. Okay. And this equation further we can modify it with H vector is equal to B vector by mu. So if we use these two relationship in this equation, we can convert this equation in terms of E and B. Okay. So let us write del cross H. Instead of H, we are going to substitute B by mu. So B by mu, which is equal to J vector plus dou d by dou t. Instead of d, we are going to substitute epsilon E. So here the epsilon, we can take it outside, dou E by dou t. So in this equation, okay, and one more thing is we can bring this mu to the right hand side, okay, so that it will be convenient for us to apply the equation. So del cross B is equal to mu J plus mu epsilon dou E by dou T. So in this equation, let us apply the equation number. So substitute equation 1 and 2 here. So if we substitute equation number 1 and 2 in this equation now, del cross, instead of B, we can use the equation number 1. It is del cross A. Instead of B, we can write del cross A, and the right hand side mu into J epsilon and mu epsilon dou by dou T, and you can use the second equation for E. E is minus del V minus dou A by dou T. Okay. Okay. Now we know a vector identity, that is curl of A, can be written as del of del dot A minus del square A. That is equal to mu J plus. Now we are going to we are going to multiply these two terms. Okay, we are going to expand this. What will happen? Mu epsilon dou by dou T of minus del V, and again if we multiply the second term, mu epsilon dou by dou T of minus dou A by dou T. Okay. Now let us split the equations again. Now let us rearrange it. Mu J vector plus, sorry, plus won't come, I think. Yeah. Now if we bring this minus outside, we'll get minus, and this del operator also outside. So that means del of mu epsilon dou V by dou T. Okay. The next term also we have minus mu epsilon. Here we have del. Okay, when we multiply these two, del by dou by dou T, we get dou square by dou T of A vector. Okay, so in this equation, rearrange all the square terms, that is all the second order power terms to the left side and the remaining terms to the right side. Okay, so if we bring every second order term to the left side, so this equation, in this left side we keep the del square A term, and in the right side we have second order term here, so we can bring it here in to the left side, that mu epsilon dou square A by dou T. Okay, so these are the two terms that is having the power of 2. Okay, so we can make the remaining terms to the right side. Okay, so that is mu J vector and minus del of mu epsilon dou v by dou t. And again we have one more term in the left hand side. We have to move to the right side. That becomes minus del of del dot a vector. Okay, and one more thing we use is we can take the del or the gradient, yes, gradient term as a common. So mu into j minus del of. Okay, so we can have mu epsilon dou v by dou t plus del dot a vector. Okay, now if you want to find the homogeneous, or sorry, it's non-homogeneous wave equation, we must bring this term to be 0. Then only we can get the wave equation, because as I already said, wave equation means the equation, it will have the second order derivatives. Okay, but so if we have to remove or make the first order derivative terms to be 0. Okay, so let mu epsilon dou v by dou t plus del dot a is equal to 0. Okay, if I let this term to be 0, then I will get the non-homogeneous wave equation. So let us apply this term as 0. You can rewrite it. We'll get minus del square a vector plus mu epsilon dou square a vector by dou t square, that is equal to mu j vector. Okay, so we'll do some adjustment. We can bring or we can take negative common and we can bring it to the right side. So finally del square a vector minus mu epsilon dou square a by dou t square is equal to minus mu j vector. So this equation is known as non-homogeneous wave equation. Okay, so the wave equation, because it is having only the second order derivatives. And why it is non-homogeneous? The right hand side we have a non-zero value. Because of this equation is known as non-homogeneous wave equation, and we have everything in terms of a, so we can conclude this equation as non-homogeneous wave equation of vector potential. Okay, similarly we have to write it for scalar potential, that is v. We have to find non-homogeneous wave equation for scalar potential also. So when you look back, in order to find the non-homogeneous wave equation of vector potential, we use this Maxwell's equation, the second law of Maxwell's equation. And in order to find the scalar potential, we need to use the third law of Maxwell's equation. So the third law of Maxwell's equation is called the Gauss law, that is del dot D is equal to rho. So using this equation, we are going to find the non-homogeneous wave equations. Okay, so similar to the previous, so here we have applied equation 1 and 2 here, and here we don't have any b term or a term or h term. Yes, so we use only the equation number 2 here. The equation number 2 is E is equal to minus del V minus dou A by dou T. So again, here there is no E term, but we know a relationship that D is equal to epsilon E. If we substitute D is equal to epsilon E, we'll get the E term. So how will you write? Del dot, instead of D we can write epsilon E. So I'll bring that epsilon to the right side, so it will become to the denominator of the right hand side. So the equation becomes del dot E is equal to rho by epsilon. So this is the new equation of Maxwell. And in this equation, if we use the equation number 2 that we have found previously, so that is minus del V minus dou A by dou T. So substitute here del dot minus del V minus dou A by dou T. Yes, that is equal to rho by epsilon. So similar to the previous case, let us split this bracket term. That is minus del dot del is del square V, and again one more minus minus del del dot dou by dou T. So I can write del dot dou A by dou T. Okay, that is equal to rho by epsilon. So here in both the terms we have minus, so we can bring that minus common. So minus del square V, and we can interchange these two like plus dou by dou T into del dot E. Okay, that is equal to minus, sorry, rho by epsilon. So here we can bring that minus to the right hand side. So the equation will become del square V plus dou by dou T of del dot A is equal to minus rho by epsilon. Okay. So in this equation, we have del dot A term, so that we have to replace by using the condition, okay, that we have derived. So in order to make them wave equation, we have set all the first order term to be 0. So if we use this equation, what we get, if I find del dot A from this equation, I'll get minus mu epsilon dou V by dou T. So this equation I'm going to substitute here. So instead of del dot A, I'll substitute minus mu epsilon into dou V by dou T. So let us write it again. Del square V plus dou by dou T into, instead of del dot A, I'll write minus mu epsilon dou V by dou T. Okay, that is equal to minus dou by rho by epsilon. Okay, and again if we make some rearrangement, del square V minus, okay, if we rearrange this, we can bring the mu epsilon term outside the bracket, and we have two dou by dou T terms, so it becomes dou square V by dou T square, that is equal to minus rho epsilon. So this equation is known as the non-homogeneous wave equation of scalar potential, because this equation contains scalar potential terms and it contains only the second order derivatives, and the non-homogeneous because it doesn't have any zero at the right side. So this equation is known as non-homogeneous wave equation for scalar potential. So if you look back, look at the equation, two equations. The only thing that is changing is, instead of J or the current density, the scalar potential is having the charge distribution, and instead of the mu, the reciprocal of epsilon is there. So the only difference is there between these two equations.